You'll get to see quite a bit today, so don't worry. But the rectangles are always on the AP in some way, shape, or form. So hang in there. But you laughed too distinctly. What? That was Callie.
It was not.
Oh, that was nice. No, I meant the one from a little while ago.
Yeah, I was like whispering, laughing. You couldn't even hear it.
Alright.
Yeah, it's
It's okay, your personality. Alright, so this page is basically saying, in order to find this area precisely, we cannot use geometry, right?
Right.
Which begs the question, hold on, pause. There are some that can use geometry, true?
Yeah.
Okay, so give me just a second. We're going to do a quick little timeout. Not totally timeout. A quick little diversion. Let me insert a page real fast. My question to you is, you don't necessarily need to write things in your notes, but we are building up to something we need to add to our forevers. When can you solve for area using geometry? And maybe I should say exactly, meaning not just an approximation. What kinds of functions could they give you technically in an integral? Because remember, we're just starting to see this whole definite integral notation and starting to relate it to actual area under a function. What kinds of functions can they give us that we can solve exactly using geometry, don't need calculus at all? Linear. So what if, first of all, they give us a linear function? Hey, if you have your forever cards, open up to forever number 2, basic graphs. Do we have a linear function in that card? Yeah. On that card. A linear function is y equals mx plus b. A basic linear function would have some sort of slope to it, and wherever you cut that a to that b, which are going to be vertical lines, you're going to have some sort of geometric figure. It might be like a rectangle plus a triangle, aka a trapezoid, but you'll have some sort of geometric figure. What other graph from that card would also result in a geometric figure?
What was
Yeah, which is still linear. We'll go ahead and keep it, but yeah, the identity function, that would also be one. What else? I see you guys looking at that card. What other functions would give a geometric area? Absolute value of x, which would be technically a piecewise. An example of that would be absolute value of x. The reason I'm saying that is because absolute value of x squared isn't going to be geometric, so we can't say all absolute value, but we can say absolute value of x, wherever you would shade that, wherever that would be cut. In some way, shape, or form, you'd have some sort of triangular area. That's true. What else in that card?
You do constant.
Yeah, constant. In a way, it kind of goes under linear, but yeah, I agree. Y equals some sort of constant, C or D. That would be a horizontal line. That would be either a square or a rectangle, depending on where you cut it. What else?
kind of shape?
Curved could be if it was circular. Struggle is square root doesn't really have a circular curvature, so that's kind of illegal. Keep thinking though. What else is on that card? Yeah, actually.
Never mind.
No, which one? Is that this?
Yeah.
Okay. No, that's good though. Linear identity, constant piecewise, the absolute value piecewise. There's actually another piecewise one that would work. Yeah, the step function. Good. Either one bracket or two brackets. Last year it was two brackets, this year it was one bracket. This brings up an interesting idea. Let's see, the step function. Let's do like 1 and 2 and 3 and 1 and 2 and okay, there we go. The step function doesn't jump up a step until you have the whole number. So like 0.5, 0.6, 0.7 still stays being 0, all the way up until you get to 1. And then 1.1 all the way up, 1.9999999 stays at 1 until you actually hit 2. Then it goes up. Pretend that was a straight line in the middle. It wasn't very straight. It was more curved. Anyway, this brings up an interesting question. What do I do even though this function has a hole? Let's say I was to find the integral from 0 to 3, so from here to here. Do you guys see rectangles? Yeah, me too, right?
Oh.
There's a rectangle, there's a rectangle. Hey, wait a minute, what's this guy's area? 0, because he's all the way down. He's not up at all, right? So that's just 0, plus this guy plus that guy would be the area, but the struggle is, does the hole mess me up? Question. Area measures, or is a measurement of what types of figures? Oh, 2-dimensional. Volume is 3-dimensional. Length would be 1-dimensional. So if area measures 2-dimensional figures, would a line be a problem? Because the whole is just one point in time, one linear dilemma, right? Would a line be a problem with area? Because does a line have any depth? The line has no width, the line has no depth, the line has no area. So even though there's a hole right here, and that boundary might be missing, does that give us any sort of dilemma? No. So that this kind of discontinuity, this kind of hole, is in a sense removable discontinuity. No, it's not removable. But this kind of discontinuity is not going to pose a problem for area. No big deal, because that line, that boundary, doesn't actually add or subtract from the area at all. So let's go ahead and ask another question. What if I was to give you, and don't worry, this will show up later, but what if I was to give you then this integral? How would you answer the integral from a to a of any function? What would that be? Mm-hmm. Why would it be 0? Yeah, you can't have any area if you don't go any depth, or you don't go any width, or you don't go any distance, right? So therefore, from A to A, have you gone anywhere? All you have is a line. All you have is a dimensionless, well, I guess you should say a widthless, first dimensional figure that has no area. So therefore, the area would be. So did you get the sweatshirt from? Which one was this? I think this was BC last year.
No, it was 2 years ago.
2 years ago.
Oh, I get it.
You get it?
Oh, wow.
Yeah, they put the purple car with rubbers and others, and they had calculus geek on the front, which was cool.
Yeah.
It was easy one. So what's it mean if it says after the hours of sleep?
0.
0.
Oh,
Exactly.
Thanks, Rahul.
So the integral from A to A, 0. Because there's no depth, no width, no distance being covered. Okay, now let's go back to what we were talking about though. There's one more type of function. There's one more type of function. This will always equal 0. It's a property, don't worry, we'll write it down in our notes. Section 4.3, I think. There's one more type of function that we have left off, but I mentioned it, we just haven't actually stated his equation because he's not on your forever card yet. He's not on your forever card yet.
Yes.
So what other type of geometric area could show up if it's not linear, not triangular, not trapezoidal, not rectangular or square? What other kind of area can we solve with a geometric formula? Circular. But how are circles going to show up? First of all, it won't be a function if it has a top and bottom part to the circle, so really we're just looking at a semicircle. How would a circular function, it could be shaded to be like a quarter circle or a half circle. Anyway, how could a circular function show up? What's the equation, basic equation of a circle? Plus y squared is r squared. But we need to get y by itself, so then guys, take that equation, get y by itself. What do we have?
My negative x squared minus r squared.
Plus r squared?
That's
Exactly. We need to add this to our forever card. Now, some of you used up literally all of the space on the forever card. So you're going to put this guy, because he's so important, underneath the title, nice and centered on the other side. Whoops. Forever card number 2, the one with basic graphs. The one you don't have any room on. And those of you who don't have any room, good job. You portioned your space quite well. Flip it where you have the basic graphs title. And this one is so important, you can put it right underneath, nice, neat, and centered, and say this guy shows up on the AP and is pretty tricky. So, if you have a negative R, if you have a positive R, now you need another positive R, then we need a semicircle. It's not a parabola. Because a parabola is not necessarily a circular arc. It's an arc, but it's not a circular arc, which means we can't even do like area of a sector, those sorts of things we learned in pre-cal before, because that needs a circular curvature. Parabolas, square root functions, trig functions, they're not circular in nature.
Can they be? Like an instance where it can be, or is it
Well, the dilemma with a parabola, remember a circle needs a constant radius, and you guys learned last year the tangent lines to parabolas and like the foci and the directrices and stuff, and remember how that distance is always changing? So that's why we can't. But a half circle, the radius will be constant everywhere within, so then we're able to use it. So this is the function. Circular could technically say semicircular, I guess that would be a bit better, or a semicircle. I don't know whatever you want to name it. You need to get into your forever cards, into the basic graph cards, and if you don't have room because you were very nice and neat and precise with how you did it, no big dealio. Put him underneath the title. And speaking of underneath the title, since we're talking about this card, this has nothing to do with integration or area necessarily. It actually has to do with limits, but there is one more function that we need to add. You're welcome. But you can actually add him to the tangent graph in a different color. You can actually add this guy to the tangent graph in a different color, because this one is the tangent inverse, y equals tangent inverse of x. I see this more on the BC exam and the BC practice, but it doesn't mean it can't show up on yours. It's a pre-cal function. Tangent inverse. Remember inverse functions, how they take a function and they flip him across the y equals x line. So tangent has vertical asymptotes at pi over 2, negative pi over 2, and pi over 2. Tangent inverse, since everything flips, is going to have horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. And the reason why this can sometimes be brought up on AP stuff is because without you being able to solve for it by hand, they could ask you for a limit of tangent inverse to infinity or negative infinity. It should equal a very particular constant, pi over 2 or negative pi over 2, and if you don't know the graph, you wouldn't be able to solve. So the time I see this come up is in a limit problem or a horizontal asymptote problem, asking for the horizontal asymptotes of tangent inverse, or asking for the limit as x goes to positive infinity of tangent inverse, which would be positive pi over 2, or negative infinity. Once again, this is more of a BC idea, but since we're already adding a graph anyway, this one you can add in a different color to the tangent graph if you would like, or since you're making room for circular, you could try to make room for the tangent inverse as well. Okay? Okay. With that, let's go ahead and come back to the non-geometric ones. And that's what this whole rectangle method is for. You could also call approximating with Riemann sums, a Riemann sum approximation. Our book really brings up Riemann sums in section 4.3. But the method that we're going to look at today does have tie-ins to 4.2. So I'm going to go ahead and zoom in on the example. This is a general idea of what our goal is. To take a distance A to B, which we're going to find by subtracting A from B. B minus A is the distance. We're going to partition that into n pieces. If they want 4 rectangles, we'll split it into fourths. If they want 8 rectangles, we'll split it into eighths. If they want 20 rectangles, we'll split it into 20ths. We partition this distance into this many subintervals, into n subintervals, by dividing. That delta x is going to be the same thing as our base, our bases of our rectangles. And then as we go to find the area of our rectangles, base times height, our bases are going to be found by the delta x, which if we find the delta x ourselves, it'll be nice and equally spaced. If they give us something like a table where they get to choose what x's they give us, it might not be equally spaced, and so all the bases might be different. But if we're making it, we're going to make them nice and equally spaced. And then all of the heights are going to come from the function values, but that I need to go into a little more depth about. But after we go ahead and add up together, if you guys can't read this bottom one, is a to the n. After we find the areas for the n rectangles, we would add them all up, and that area, whatever that is, would approximate the definite integral from a to b of f of x dx. And the more rectangles we have, the better the approximation. Okay, and that brings us up to this page. Here's the idea. If we take this b minus a distance, and if we partition it, if we split it up into n pieces, I'm going to have this example, x1 to x, whatever I have, 2, I think. This will be our example. I'm going to go ahead and kind of denote what's going on as far as splitting it up. Let me zoom in. Let's say this x1 to x2 is one of the partitions, just one of the intervals within this bigger interval that we've formed. If this x sub 1 to x sub 2, that's why I didn't name it a and b. Now I remember. If this x1 and x2 is one of those partitions, one of those pieces to the larger whole, we have a dilemma because when we go to do our rectangles, a rectangle needs a base, and that's no big deal. The base will be x2 minus x1. The same thing as delta x, but we could just say x2 minus x1. The base says subtract the two x's, the distance between them is the base. No big deal. But the problem for rectangles is we also need a height. Now imagine this curve right here, and if I was to go between, say, 0 and 1, and if I was going up, what do you guys think is going to bound the rectangle, is going to keep it from going just forever? We'll just say the curve to start. Is that okay? The curve is going to stop it. Now, question. Am I going to stop when any piece hits the curve? If that was true, when would I stop? Right here. I would start at the right-hand endpoint of that partition, and I would make a triangle or a rectangle. If I wasn't bound by when I first hit the curve, I could keep on going to how high? To up there. So here's the idea. When we're doing rectangles, the question is, when do you stop? Because at some point you have to stop, and since this function is not linear in nature, at some point I have to stop and make a rectangle, and I'm going to leave some people out. Or I'm going to include more than I should. So the idea is for these two, when I go up, when do I hit? Well, for a left approximation, just for one representative area, we could say that A would equal delta x, which would be a base, x2 minus x1, times, for this subinterval, because where do you think I'm going to hit? Am I going to hit using the x1 if it's a left-hand approximation, or do you think I'm going to hit when x2 hits the curve? Oh, wait, why should we have said x1?
Because it's the left.
It's on the left. Literally, it's that easy. When I mean left-hand approximation, I mean for every, or a left Riemann sum, what I'm saying is for each individual partition that we have that we're making rectangles in, are you going to choose the guy on the right or the guy on the left to hit the curve as your height? I'm going to choose for the left-hand one, the guy on the left. That's the x value I need to plug in. Because that's the one, for instance, in this example, for this partition, that's the one I'm going to go off of, is when it hits from the left. We're going to get back to this in just a second, but what do you think is going to change for this little representative subinterval? What's going to change when you go to do the right? Do I still have the same base? Yeah, the same delta x, no big deal. But what am I going to plug into my function this time? X of 2. Now here's an interesting question. What about midpoint? Does my base change?
No.
No, it does x. But what am I going to put inside? Yeah, you could think 1.5, but that's not necessarily 1, that's not necessarily 2, it's just somebody unknown. So mathematically, how do we get to the middle of something? Think midpoint formula, or think averaging the two together. Same idea. We need the midpoint, or we need the average of the two. You could almost think x2 minus x1 divided by 2, but that would just be the distance. I'd have to add that, plus you back to x1, it gets complicated. The easier way to think is just the average between the two. And that one, we would then go ahead and have this additional guy that we would then go up and hit the curve at. So let's go ahead and visualize that with the following example. We have the function 9 minus x squared. We have the interval 0 to 3. And guys, how many rectangles are they asking us to fit into this interval? So I'm taking myself out of the picture for just a second. Another reason I'm doing that is because you don't always need the picture in order to be able to solve this problem. Actually, if they were to ask this on an FRQ, which they frequently do, they do not expect a picture, and they will not give you one. So here's how you can think about it. If I'm going between 0 and 3, and if I'm splitting it up evenly, I need to make 3 partitions, couldn't I think of, okay, take the distance, that looks the same as what I just did. Take the distance, 0 to 3, which is 3, right? I find that from doing 3 minus 0. And I'm going to cut that. Delta x is b minus a all over n. I'm going to cut that into how many pieces? 3. So I'm going to be going by 1, right? Which is super obvious, I know. But what if they had said n equals 6? What would I be going by?
2? Oh yeah. 1.
b minus a, good, over n. So it would be 3 minus 0 over 6, which would be going by halves instead of by 1. What if they said n equals 8? 3 eighths. Are you guys tracking how close I got there? Because it'd be b minus a, 3 minus 0, cut into eighths. So going by 1s is super, super easy, because it's like, oh, okay, my partitions are from 0 to 1, from 1 to 2, and from 2 to 3. No big deal. But if I was going by eighths, it'd be 0 to 3 eighths, 3 eighths to 6 eighths, 6 eighths to 9 eighths, 9 eighths to 12 eighths, 12 eighths to 15 eighths, 15 eighths to 18 eighths, 18 eighths to 21 eighths, and 21 eighths to 24 eighths. Whew. And 24 eighths is... So whatever they give you, no matter how messy it is, you can always take the distance, b minus a, and cut it into those intervals, and jumpity jump, jump, jump by those partitions, or by those intervals, right? Now, is this one easy? Pretty easy. Because I can go ahead and say, okay, cool. So I have my 1, I have my 2, I have my 3, right? And thinking about 0 to 1, wait, I already hit it 0. Why did I do that? Because this is a left-hand approximation. Okay, we're doing a left-hand approximation. So between 0 to 1, we hit at 0, and we're going to go over a width of 1. So the function value at 0 establishes the height for that rectangle. Now I still need to get into this partition from 1 to 2, so where am I going to go hit the curve this time? On the left. I'm going to hit at or when x equals 1. Establish the height for the rectangle to come. There we go. Does that make sense? Now I have the partition from 2 to 3. Where am I going to hit? This is a left-hand approximation. So from 2 to 3, I'm going to hit on the left. I'm going to hit at 2 and establish the height. You guys see where these specific rectangles came from? Took the 3 to 0, split it into thirds. So I would have 3 rectangles. And then when I was coming up, I said, oh, go until the left hits and then establish. Go until the left hits, then establish. Go until the left hits, then establish. Maggie.
Do we always just go to the left? Like, do you always just left face off? Or do they
When they say a left Riemann or a left-hand approximation, will come from the left.
Okay.
So, the picture shows it. The math could show it too, because I have how many rectangles?
3.
For each rectangle, the nice thing is, all of them, base times height, right? All of them have a base of what?
Third, 101.
All have a base of 1. B minus A all over N. So the first rectangle, base of 1, what's its height going to be?
Is that 9?
Why is it 9? Because that is the function's value at 0. Plug in 0, 9 minus 0 is 9. You're totally right. It is a height of 9. We'll get there in a second. For the second rectangle, base is 1 again, but when did I hit the height?
8.
When I was plugging in 2. No, not 2. When I was plugging in the left. When I was plugged in 1.
Yeah, that's.
So that'd be f of 1. And then for the last one, I would have a base of 1 and a height of f of 2. You guys see how I just started on the left at A, and I just counted up by my delta x's, 0, then 1, then 2. Why not 3? I already have my rectangle. I don't need to do 3. Now here's the cool thing, the AP doesn't need you to draw a picture, the AP doesn't need you to even write out the snazzy A1, A2, A3, although my brain kind of, I don't know, understands that a little bit easier. But what you could also do is say, hey, my left Riemann approximation is equal to 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2. That's the work I want to see. Now technically, does the expression up above show that exact same thing? Yeah. But you only need to write it out once. So you could just write it out, and then at some point you have to go back and say, wait, I have a function. Wait, I have heights. And wait, I need to plug in. But it's always a good practice to start with your function notation first, if possible, and then plug in. For instance, some of you guys already noticed that f of 0 is what?
9.
So 1 times 9 is going to end up being 9. F of 1 ends up being 8. 9 minus 1 squared is just 9 minus 1, which is 8. And then f of 2?
It's going to be
5, because 9 minus 2 squared is 9 minus 4, which is 5. If this was an FRQ, I would tell you stop, don't you dare, because believe me, at one point or another, your addition fails.
So does it?
Exactly.
Just square them? I mean, just like put a square around it.
Mm-hmm. As soon as you have a numerical representation, you don't have to fully simplify it for the FRQ. Now, if you were checking with the back of the book, or if you were trying to compare to other approximations, would it be a good idea to have something to compare and be thinking about how the actual approximation for the integral, using the left hand,
Or
box. No, I'm
And that
not
is why we box it before you add.
Exactly. You're double checking me, that's good. But we do end up with an over approximation of 22. How do I know this is an over approximation of the actual?
you went over
I went over the curve. Does anyone know why I went over the curve? What characteristic of the graph made it an over approximation? It is left, but what characteristic of the function? It's a negative parabola. So, I wonder, is it the concave downness or is it the decreasingness? And yes, they are different. Let's try. If we were to do left over here, because this part's increasing in concave down. If I were to do the left, is it an over approximation? It's an under approximation. So it's not the concavity. It's the decreasing nature of the graph that makes it an over approximation. Interesting. Alright, guess what time it is? Time to come to the right.
That makes sense, because I'm like, doesn't it like, when you do both of them, doesn't it kind of like balance out? Because if it's increasing, it's under approximation, and if it's decreasing, it's over approximation, so it's kind of like filling this one. If we were to do like all
Like on either side of a parabola because of the symmetry?
Uh-huh.
Yes, but the dilemma is
and it's still,
that we're only going from 0 to 3. Ash.
Why was it 5 instead of 6?
because 2 squared is 4 and 9 minus 4 is 5. So from the right, I have to do my exact same partitioning because I'm still going from 0 to 3. I'm still cutting it into 3 subintervals. The nice thing is I still am going to go by my 1s for my delta x. But this time, instead of hitting between 0 and 1, because I have to come up, instead of hitting at 0, where am I going to stop my rectangle? Establish the height and go back. So between 0 and 1, my 1 is what's going to establish the height. When x equals 1 hits my function is the height for the first rectangle. What's going to be the height for the second rectangle? When 2 hits the curve, establishes the height for the second. And then, wait, but 3 is 0. Okay, well, I have a flat rectangle. Nothing there. Trevor, hang in there, bud. So each of my bases are what? Yeah, I'm still going by 1s, right? Because I'm still just saying n equals 3, so I'm just going by 1. So each of my bases will be 1. You guys good? Just fill them all in? Mm-hmm. All of my heights are going to be f ofs because they were bounded by, or restricted by the function. Now, we could say, forget the 0, go forward to 1, and then 1 and 2 and 3. We could say we hit at 1, we hit at 2, we hit at 3. But sometimes a shortcut, to make sure you don't get messed up, is instead of starting from the left-hand side of the number line and counting 0, 1, 2, start the right-hand side and go 3, 2, 1. We only have 3 rectangles, and this way it keeps us honest. Why not 0? Well, the rectangle's already been formed. When you get to 0, there's no reason to hit there. Now with this, kiddos, once again, we could say that the right Riemann approximation or the right-hand sum if I put a P in there, if I could spell right, is equal to. You don't need to write it in a snazzy table form. You could go ahead and just show it as one line, like what you would put into your calculator if you were able to use it, which is rarely true on one of these problems. But at some point, you got to plug into the function. This is all notation until we apply it. So therefore, plug in 3. What do we got? 0. Wait, 0? I don't get it. So there's a rectangle with 0? Yeah, remember he hasn't gone up anywhere because 3 hits, so then that was just flat. So 0 plus, how about plug in 2? 5. And then plug in 1? 8. This approximation, you should box it here if it was an AP and don't even try to simplify. But if it's a back of the book problem, you gotta check it. If you're trying to compare it, etc. 13 would be our right approximation for the integral 0 to 3 of our 9 minus x squared dx. But there's 3. We've done left. We've done right. What's left for us to do? Midpoint. So midpoint, 0 to 3. We're still doing our 3 minus 0 cut into thirds, so we still have our delta x equaling 1. But the problem is, when we do each of our subintervals, we're not allowed to hit at the left or the right. We need to hit at the middle. So what's the middle of, or the average of 0 to 1? 1/2. What's the average between 1 and 2?
1.5.
1.5, or 3 halves. Average between 2 and 3? 2.5, or 5 halves. So when we come to do our midpoint approximation, a lot of things are going to be super similar. We still have A1, we still have A2, we still have A3. We're still going to do our base of 1 because that is still exactly the same. We're still going to do our heights using function values, but for my first partition, which has endpoints of 0 and 1, am I hitting at 0 or 1? Nope, where am I hitting? At 1/2. Which means I hit and I come back under a little, over a little, and I have my rectangle. In between 1 and 2, where am I hitting?
3.5.
3 halves. 3 halves. And then where's my last one going to be?
5 halves.
5 halves. Just from the picture, guys, which approximation do you think is the best? Midpoint. But the nice thing is for actual integration and for solving exactly without using area and the approximations from rectangles, the limit definition, if you fit infinitely many under, all three types of approximations will all approach the exact same area. So here we have the midpoint Riemann approximation equaling R1 times f of a half plus 1 times f of 3/2 plus 1 times f of 5/2, which ends up being, ready?
Yeah.
1 times 9 minus 1/2 squared plus 1 times 9 minus 3/2 squared plus 1 times 9 minus 5/2 squared. If this was an FRQ, what do you think I want you to do?
Oh, that's nice.
Exactly. Which I do believe it ends up being, if I remember right, 20, no, that's not right. 37/4? I think it's 37/4.
You get on the test?
If it's a long answer. Now, hold on, pause. This ends up being, I believe, ooh, nope, I'm totally off on this. Hold on. I think it's 73/4. This ends up being 18 1/4. Tomorrow, we're going to see just how close it is, because we're going to tie together the idea of an antiderivative and a definite integral, and how that can actually solve for this area without using the rectangles. Dilemma is rectangles are important. Oh, I erased it, or else I'd show it to you for those of you guys that are curious. Anyway, happy Monday. I'll see you guys later.